So we're now going to talk about the Hilbert space as a continuation of this revision lecture. And this is a very important concept because that's where our vectors occur. So let's start by defining it. A Hilbert space is an abstract vector space possessing the structure of an inner product. In the previous lecture, we have discussed what an inner product is and what a vector space is. So we're going to consider now that we have an abstract vector space, which is the Hilbert space, and this has the structure of this inner product. And the key idea here is that each quantum state of the system is going to be characterized by a state vector in this complex inner product space, which is the state space. Now, we know this Dirac notation, and one important point here, because I see a lot of people get this wrong, is that this notation is more general than describing the system in terms of wave functions, because we're going to see later on in our course that a wave function is a component of this ket psi if you take wave function psi r in the R representation, and if you take the wave function psi p, it's a component of this vector psi in the P representation. If you want to think about it, this is like when you have a vector and you describe this in Cartesian coordinates or polar coordinates or spherical coordinates, whatever you want. You cannot mix up the two things. And if you would say that you would have something like that, that's what precisely would be doing. I've seen this a lot. And I would like to call your attention that this is simply not correct. This is wrong. We're going to see later on why you cannot write ket psi r or ket psi p. But the key idea is that a ket is something more general than that. So please don't do that, but be aware that a lot of people use this kind of misconception. And we're going to discuss this later on in the course. Why not? When we define position and momentum representation. And if you're curious, you can have a look at Comentanucci di Villaloe, chapter 2, Quantum Mechanics. It has a very good explanation, especially in the complements. And the Dirac notation is not only general for this basis where you have the wave functions, but it can also be used for discrete variables, in which case you wouldn't be able to describe your system as a wave function. So just to summarize, the notation that we have is we have this ket psi, which is a vector in the state space. Then there is the bra psi, which is the dual vector to the ket psi. And you can calculate also inner products between two vectors in state space, which are defined in this way. So you have a scalar in the end, but this is a kind of product in which you had two vectors and you obtained a scalar, so it's an inner product. For instance, if you want to see how the Dirac notation can be used for discrete variables, have a look at the spin-half particle. I mean, this particle defines a state space which is two-dimensional because it has two base states. So you can have spin up, which corresponds to L equal 1/2 and M plus 1/2. And you have the other case, which is S and MS, not L, it's not the orbital angular momentum. Spin angular momentum. So you have spin up and spin down, and you can write an arbitrary state using spin up and spin down, where then you can say that this are the basis set, and you are spanning these, and you have to guarantee that this is normalized. Now moving on, there is also the concept of subspace. So what is a subspace? If you have a vector space V, a subspace is going to be a state containing some of the vectors of V, but it has to satisfy all the properties of a vector space in its own right. So in particular, you have to have, the space has to have the zero vector, and also vectors in a subspace. They have to be closed under addition and scalar multiplication. So if you have two vectors, for instance, in a subspace W of a vector space V, given any two vectors in W, V1 and V2, we know that V1 plus V2 is also in W. So it's something that is self-contained and behaves like a vector space in its own right, but is a subspace. For instance, if you consider these two vectors, these column vectors here, you see that they define an orthonormal basis for a subspace on the z equals 0 plane in R3. And if you think about the plane, xy plane, you see that in fact it satisfies all the properties of a vector space that I'm talking about here above. So you can actually ensure that it is a subspace. Also, you can represent vectors as a column in the state space. So for instance, if you get an orthonormal basis phi j, where j goes from 1 to n, then you can write an arbitrary ket as a coherent sum of that. But you can also write it as a column vector. And if you want to go and compose the bra, you have to get the transpose conjugate of the column vector. And you have also to apply conjugation when you construct the bra for the ket which you have above. So you can really see that there are several ways of writing a state vector. And another concept that is very important in quantum mechanics is the concept of operator, because an operator acts on a vector space, and it is a function who acts on a vector in the space and returns another vector in that same space. So it kind of modifies the vector, but it keeps it as a vector. For instance, you have ket psi and ket psi dash. When you apply this operator, you get psi dash is equal operator applied to psi. Now, this is often represented with a hat when we need to distinguish from classical variables or scalar quantities. This is a linear operator. So if you know, this is not always a linear operator, but if you want to define a linear operator, you have to guarantee that this property below holds, which is linearity. And with operators, you have to be careful how you apply them, and you can apply them sequentially. For instance, here we have O1, O2, O3 applied to psi. First we applied O1, then we applied O2, and afterwards we applied O3. So you see, depending on how you apply them, you may or may not get the same result. And that's why we need to have a look at commutators, because the order can be interchanged, and then we can have commutation on. If we calculate the commutator of A, B, where A and B are operators, and this commutator is 0, this means that it doesn't matter if you apply A first or B first. However, if it's not 0, then you cannot proceed with impunity. So in this case, they can be interchanged, but sometimes they cannot. So now we're going to talk about something that is also very important, which is the closure relation.